You're watching a machine crawl down a raw, dirt-packed stretch of land, and in a matter of minutes, it leaves behind a perfectly poured slab of reinforced concrete. No hesitation, no uneven lines, no wasted motion. This isn't just roadwork. It's industrial precision unfolding in real time. This is how roads are built in the United States today. And the difference isn't subtle. At the heart of it all are machines that look like they belong in a factory, not a construction site. If you enjoyed this breakdown, don't forget to like, subscribe, and drop a comment. Your feedback helps shape what we cover next. And you being here keeps the conversation going. Thanks for watching. See you in the next one. Laser-guided slipform pavers, GPS-controlled graders, and automated rebar placers aren't gimmicks, they're the core of a system that can turn undeveloped ground into durable, load-bearing highway with minimal human error and maximum speed. This process doesn't start when concrete hits the ground. It begins with the foundation. Crews first survey the land using terrain mapping tech, then remove excess soil and level the site using graders synced with satellite data. These GPS-guided machines don't just scrape and push dirt. They follow precise digital models that factor in slope, water runoff, load requirements, and long-term stability. After grading, crews reinforce the base with compacted layers of crushed stone or gravel. In some environments, like deserts, soil stabilization becomes essential. That means injecting water into dry, loose sand to bind particles together before compacting. The result? A subbase strong enough to support multi-ton paving equipment and, later, endless waves of traffic. By the time it arrives at the job site, it's not just wet cement. It's a custom-engineered mixture, ready to perform under years of wear, freeze-thaw cycles, and heavy freight movement. Now enter the slipform paver. This machine doesn't just pour the concrete. It spreads, vibrates, shapes, and finishes it all in one continuous pass. With sensors scanning its surroundings and digital systems adjusting the pour in real time, the paver ensures that every inch of road surface meets exact tolerances. Laser controls maintain elevation. Internal vibrators eliminate air pockets. And an automated rebar system inserts steel rods as the machine moves, reinforcing the slab with precision. It's not unusual for these setups to lay down multiple kilometers of roadway in a single day. That speed is staggering, but what's more important is consistency. Human crews would struggle to maintain this level of precision for even a few hundred meters. These machines can do it indefinitely. Once the concrete is laid, the process still isn't over. Crews must cut expansion joints at specific intervals. These joints allow for thermal movement, preventing cracks during hot and cold cycles. Afterward, they're sealed to block water from penetrating the base layers, a critical step for long-term durability. Curing is next. A mist or compound is sprayed over the surface to lock in moisture and control the drying process. It's not about drying quickly. It's about drying evenly. Fast drying leads to brittleness and microfractures. Controlled curing strengthens the slab from within. For several days, the road is left untouched. No cars, no pressure. Only once the concrete reaches its full strength does the road open for use. Final inspections follow, verifying the surface flatness, checking for joint alignment, testing strength, and ensuring adherence to all design specifications. This contrast underscores the global divide in infrastructure technology. In China, the situation is different again. The country's massive infrastructure projects have forced innovation, especially when building in extreme conditions. A clear example is the highway through the Taklamakan Desert, with temperatures ranging from 25 degrees to over 70 degrees and constantly shifting sands. Building a stable road through that environment requires more than traditional methods. Engineers start by leveling dunes using bulldozers, then inject water into the sand for stabilization. The sand is compacted until it forms a semi-solid base. Heated asphalt is laid in multiple layers using high-temperature pavers built to handle the environment. Each layer is rolled and sealed quickly to prevent cracking from temperature extremes. These roads aren't experimental. They're functional highways built to connect remote regions, support economic activity, and withstand brutal environmental stress. In both the US and China, what we see is a common thread: machine-driven precision, the ability to standardize processes, eliminate variability, and produce roads that hold up not just for years, but for decades. Why does this matter? Because infrastructure isn't just about transport. It's about growth, safety, and connectivity. Roads that crack early disrupt economies. Roads that fail under weather extremes cost lives. And roads built right the first time support everything. If you enjoyed this breakdown, don't forget to like, subscribe, and drop a comment. Your feedback helps shape what we cover next. And you being here keeps the conversation going. Thanks for watching. See you in the next one. Everything from logistics to emergency response to everyday mobility. Still, advanced equipment comes at a cost. A single slipform paver might cost upwards of $300,000. High-performance batching systems and GPS guidance add more. But when you consider the long-term savings, fewer repairs, longer lifespans, faster project timelines, the return on investment is massive. The future of road construction is clear. It's faster, it's more accurate, it's increasingly automated, and it's moving toward global adoption. Whether it's in a high-traffic US freeway, a remote desert in China, or a rising city in South America, the same principles apply. Engineering matters. Machines matter. And how we build roads says everything about how we plan to move into the future. If this gave you a deeper appreciation for the technology behind the roads you travel, hit that like button. Share this with someone who's into construction, logistics, or infrastructure. Drop your thoughts in the comments. Have you ever seen one of these machines in action? And don't forget to subscribe for more breakdowns of the systems that quietly power the world around you. Because the next time you roll down a smooth, silent stretch of highway, you'll know exactly how much engineering it took to get you there. And let's be honest, most people never think twice about roads. They're just there, part of the background, until something goes wrong, until there's a closure, until a pothole takes out your axle, until a cracked surface leads to a dangerous skid. And suddenly, what was invisible becomes very, very real. That's the difference these machines make. That's what precision engineering protects you from. It's easy to forget that every road you use, whether it's a suburban street or a 10-lane interstate, exists because someone planned it, tested the soil beneath it, calculated its load capacity, and poured thousands of tons of concrete with exacting standards. And today, the process isn't being left to guesswork or gut feeling. It's being handled by machines that can do more, faster, and better than ever before. Laser-guided systems ensure that elevations are dead on. GPS controls don't just help the machine stay on course, they are the course. They're pre-loaded with digital plans that dictate slope, drainage, curvature, and thickness. These aren't just tools. They're extensions of the engineer's design translated directly into physical reality. And the consistency that results? That's the real win. You don't have one good section of road and one bad section right next to it because one crew was more experienced. You don't have one segment settle faster than the rest because someone misjudged the soil compaction. With automated systems, every stretch meets the same high standard. Every mile is as strong and smooth as the one before it. Now multiply that kind of efficiency over thousands of miles. That's the US advantage. That's why so many of its highways and interstates last not 5 or 10 years, but 30, 40, or more. Properly built concrete roads are an investment in stability, financial, logistical, and literal. And let's not ignore the economics. Yes, a laser-controlled slipform paver costs more than a manual crew, but it also finishes the job in a fraction of the time. It eliminates rework, it reduces material waste, and it lowers labor risk. Because fewer people on site means fewer accidents, fewer delays, less unpredictability. That precision and efficiency are what developing nations often lack, not because they lack intelligence or work ethic, but because the capital investment required for this level of technology is out of reach. In many countries, road building is still an analog process. No sensors, no batch plants. Concrete is mixed in pans or on the ground. Rebar is bent by hand. There's craftsmanship, sure, but also variability. And variability is the enemy of longevity. A road might look great on day one, but after a season of rain, or a cycle of freezing and thawing, you start to see the difference. Cracks appear, edges crumble, the surface warps. Maintenance becomes constant, budgets stretch thin, and traffic suffers. This is where the gap in infrastructure development becomes more than just a statistic, it becomes a barrier to progress. Because roads don't just carry people, they carry opportunity. You want to improve access to healthcare? You need roads that don't wash out every rainy season. You want to support small farmers getting their products to market? They need transport that doesn't double their costs with every axle-jolting detour. You want to build up regional trade, tourism, and emergency response? It all starts with roads. That's why the automation on display in the US and the desert engineering breakthroughs in China matter far beyond their borders. They're not just domestic wins. They're models for what's possible. The Taklamakan Highway, for example, wasn't just an engineering flex, it was a lesson. China proved that you can build through impossible terrain with the right combination of science and innovation. They took one of the harshest environments in the world and said, "We can make this work." And they did. Stabilizing sand with water, compacting it under massive rollers, and layering it with temperature-resistant asphalt, it worked. The highway didn't just survive, it performed. That project became a blueprint for building in other extreme climates, from deserts to flood zones to permafrost regions. And it's not just China. Other nations have taken note. From Middle Eastern countries looking to expand infrastructure into desert interiors, to African nations planning to bridge rural gaps, the principles are being studied and adapted. But it circles back to one key point. You need the machines. You need the batching systems that deliver consistent concrete. You need the GPS that ensures every elevation matches the blueprint. You need the slip-form pavers that don't deviate, don't fatigue, and don't introduce human error into a process where fractions of an inch matter. And more than anything, you need the mindset that values precision and scalability. Because concrete roads aren't just functional, they're foundational. They define the shape of a country's growth. They link urban centers, port hubs, and border zones. They're part of the economic bloodstream. So when a country invests in modern road construction, it's not just spending money, it's making a commitment to its own future. That's why the US continues to lead in this space. Not just because of budget, but because of the systems in place to keep the process standardized, regulated, and accountable. From federal highway standards to DOT oversight at the state level, the margin for error is small, and the expectation is clear: get it right, or do it again. And doing it right the first time? That's where the machines come in. Slip-form pavers don't guess. GPS-controlled graders don't forget elevations. Batch plants don't mismeasure water ratios. And the result is roads that hold up under punishing use, through extreme weather, across multiple decades. That's the power of automation in civil engineering. It doesn't replace people, it enhances them. It lets skilled workers focus on oversight, calibration, and problem solving instead of backbreaking labor and rework. It turns road construction from a messy, reactive process into a clean, predictable system. And for countries still stuck in the older model, this shift isn't out of reach. It's happening already, slowly but surely. Partnerships, equipment leasing, training programs, and infrastructure grants are bringing precision technology to places where the need is greatest. Because this isn't just about a stretch of highway. It's about what that highway makes possible. It's about ambulances that get to hospitals faster, about farmers who can reach distant buyers, about families that can safely travel even during a downpour. It's about businesses that grow when transport isn't a liability. And it's about governments saving millions in long-term maintenance by investing smartly upfront. So the next time you see one of those massive machines rolling across a construction site, calm, steady, deliberate, know that it's more than just industrial muscle. It's a symbol of what modern infrastructure looks like. Efficient, reliable, engineered for the future. Let's bring it full circle, because when you pull back and look at the big picture, it's more than just concrete and steel. What you're really seeing is a transformation in how humans shape the land to meet the demands of a growing, fast-moving world. Roads are one of the oldest forms of public infrastructure, but today, they're also one of the most technologically advanced. We've gone from hauling gravel with oxen to leveling terrain using satellites, from hand-troweled concrete to fully automated machines that can pave perfectly smooth highways with surgical precision. And that evolution didn't happen by accident. It happened because the need for strong, reliable roads never goes away. In fact, it only grows. As populations expand and economies become more interconnected, the demand for resilient infrastructure skyrockets. Roads have to handle more weight, more traffic, and harsher weather than ever before. And that's why the traditional methods just don't cut it anymore. In the US, every mile of concrete highway reflects layers of planning, design, and engineering starting from the dirt and working all the way up. Soil isn't just soil, it's tested, evaluated, and treated. If it's unstable, it's replaced. If it's dry, it's moistened and compacted. If it's sandy, like in desert regions, it's stabilized with water and binding agents. This foundation work is invisible to most people, but it's absolutely critical. Because no matter how advanced the paving machine is, a weak base means a weak road. Once the base is locked in, the materials come into play. High-performance concrete isn't just about strength, it's about balance. The right mix resists cracking, supports heavy loads, and withstands temperature extremes. And these aren't wild guesses or rules of thumb. Every component, water, aggregate, cement, and chemical additives, is measured down to the decimal. Everything is optimized. Then comes the hardware. Slipform pavers, GPS-controlled graders, automated joint cutters. These aren't gadgets, they're essential tools that eliminate inconsistency and allow crews to work faster without sacrificing quality. In the US, where highways stretch for hundreds, even thousands of miles, this kind of repeatable accuracy is what keeps the entire system functioning smoothly. Contrast that with the manual construction still used in many parts of the world. Without advanced equipment, the process slows to a crawl. It becomes more vulnerable to error. Concrete isn't measured exactly. Reinforcement may not be placed uniformly. Grading isn't as accurate, which leads to drainage problems and early cracking. And the cure? Time? It's often cut short out of necessity, leading to long-term durability issues. That's not a critique of the workers, it's a reflection of the tools. You can only build as well as your equipment allows. Which is why the technology used in the US and China isn't just impressive, it's important. Because it's not only solving engineering problems, it's laying down a roadmap literally and figuratively for the rest of the world. The highway built through the Taklamakan Desert didn't just serve the region, it sent a message. That no environment is too difficult, no terrain too remote, when the right techniques are applied. That kind of roadwork is what makes trade routes possible. What opens up land for agriculture, tourism, and settlement. It shows how engineering, when backed by technology, can overcome even the harshest natural conditions. This is the future of infrastructure. If you learn something new or see your daily commute a little differently, now, hit that like button. Share this video with someone who's into infrastructure, engineering, or just love seeing how the world works. Drop your thoughts in the comments. What part of the process surprised you most? And subscribe if you want more deep dives into the systems that hold everything together. Because beneath every smooth ride is a story, and this one's built to last.